Dear learners, I welcome you all to this module. The title of the module is Subspace of IN and Rank of a Matrix. In this module, we are going to learn about the subspaces of vector spaces, null space, column space, dimension and rank of a matrix. Numerous problems related to these concepts are also discussed here. Here, the set IN is a vector space under usual addition and scalar multiplication consisting of all n tuples of real numbers. The aim of this session is to introduce the learner to the notion of a subspace. Roughly speaking, a vector space is a set of objects called vectors which it is possible to add and to multiply by scalars subject to reasonable rules. Vector spaces occur in numerous branches of mathematics as well as in many applications. They are therefore of great importance and utility. Vectors have many real life applications including situations involving force or velocity. For example, consider the forces acting on a boat crossing a river. The boat's motor generates a force in one direction and the current of the river generates a force in another direction. The concept of rank is frequently occurring term in matrix theory and it is defined to be the number of linearly independent rows or columns in a matrix or the largest minor in a matrix. Computation of rank of a matrix plays a vital role in matrix algebra. One of the applications of finding the rank of a matrix is to evaluate the number of solutions of a system of linear equations associated with the corresponding matrix. We shall see some series of definitions now. Definition 1. A subspace of IN over a field F is any set H in the subspace IN that has three properties. The first one is the 0 vector is in H. For each u and v in H, the sum u plus v is also in H. And the third one, for each u in H and each scalar c in F, the vector cu is in H. In other words, we can say that the subspace of a vector space is closed under addition and scalar multiplication. That is, a non-empty subset H is a subspace of IN over a field F if and only if alpha u plus beta v belong to H, where u and v belong to H and alpha is in field F. The next definition says the column space of a matrix A is a set of all linear combinations of the columns of A. And the next definition is the null space of a matrix A is a set of all solutions of the homogeneous equations Ax is equal to 0, where 0 is a 0 matrix. We shall see a theorem now. The null space of an M by N matrix A is a subspace of IN. Equivalently, the set of all solutions to a system Ax is equal to 0 of M homogeneous linear equations in N unknowns is a subspace of IN. Proof is on the screen. We shall discuss the proof now. Clearly, the 0 vector is a null space of A. So, we have to show that a null space of A satisfies the other two properties required for a subspace. So, take any two vector u and v null space of A such that AU is equal to 0 and AB is equal to 0. Then, by the property of matrix multiplication, A multiplied by u plus v that can be written as AU plus AV, that is equal to 0. Thus, the vector u plus v also satisfies Ax is equal to 0 and so u plus v is also a null space of A. Also, for any scalar c, A multiplied by Cu can be written as C multiplied by Au and the value of Au is 0, that gives me A multiplied by Cu is also 0. That again implies the vector Cu is a null space of A. Therefore, null space of an M by N matrix A forms a subspace of IN. We shall see another definition now. A basis for a subspace H of IN is a linearly independent set in H that spans H. The next definition. Suppose the set beta containing the elements b1, b2, etc. and bt is a basis for a subspace H. For each x in H, the coordinates of x relative to the basis beta or the weight c1, c2, etc. ct such that x is equal to c1 b1 plus c2 b2 plus etc plus ct bt and the vector in IP x, that is x beta, is equal to the column vector C1, C2, etc. Cp is called the coordinate vector of x relative to beta or the beta coordinate vector of x. We shall see the next definition. A matrix M is said to be an invertible matrix if and only if determinant of that matrix, that determinant of A, is not equal to 0. The next definition says about the dimension. The dimension of a non-zero subspace H is the number of vectors in any basis for H. The dimension of the zero subspace is defined to be 0. The next definition is about the rank. The rank of a matrix is defined by the dimension of the column space of A, and it is noted by rank A. Also, the number of linearly independent rows or columns is called rank of a matrix A, and the number of pivot columns of echelon form a matrix A. We shall see some examples related to the concept that we have discussed now. Okay, so first example is, consider the set H or space H consisting of the elements of the form A1, A2, etc. k an belong to In such that A1 plus 3 A2 is equal to A3 is a subspace of F. That is what we have to prove now. So, we have discussed how to check whether a space forms a subspace of another space. So, what we are going to do is, first we are going to trying to prove the space that we are considering is non-empty. For that, I am going to have all of the A values to be equal to 0. What happens if I let all the Ai's to be equal to 0? So, substitute 0 here, plus 3 is 0, you will have 0, that is again 0. It satisfies the given condition, which means that definitely this element will be there in 0 H, because, so this value is A1, this value is A2, next value is also A3, therefore A1 is 0 here, A2 is 0 here, and A3 is also 0 here, that satisfies the given requirement. Therefore, this belongs to H, therefore, this tells us my H is not gonna be empty. So, now after finishing this, I am taking two random elements, that is alpha and beta. So, now alpha is equal to x1, x2, x3, or again for the third equation I am letting x1 plus 3 x2 because it has to satisfy the condition. I am not worrying about the rest of the entries, it can be any entries, and k I am having xn minus 1x. Similarly, for beta it should have y1, y2, and the third entry I have to be very careful because of the fact that of the given condition it is focusing only about the third entry. So, here the third entry is again y1 plus 3 y2 and k I am letting yn minus 1 and yn. I have taken two elements alpha beta from the set called H, and after that I am finding alpha plus beta. If I am able to prove alpha plus beta also there in H, there is a chance of getting H to be a subspace, right? Therefore, I am proving alpha, I am trying to prove alpha plus beta is an element of H. I am finding alpha plus beta, and you can see this is x1 plus y1, that is x1 plus y1 here, and x2 plus y2 here, and this is x1 plus 3x2 plus y1 plus 3y2, that is here, and all of the entries k plus k here I should have 2k, and then xn minus 1, yn minus 1, xn plus yn, that is how I can have. Now, so this is again an element of H because of the fact that, so here x1 plus y1, x2 plus y2, the third entry, you can see it again satisfies the given condition, that is x1 plus y1 plus 3 of x2 plus y2. So, therefore, this alpha plus beta will be again in the set given set H. Now, if you consider C alphas where C is a scalar and you have this form Cx1, Cx2, Cx1 plus 3x2 etc. up to k Cxn minus 1, Cxn belong to H. So, why is it so? Because the third entry again satisfies the given condition, it will be there in my set H. Therefore, C alpha is all belongs to H. We are able to prove alpha plus beta is an element of H and C alpha is an element of H. That in turn tells me H forms a subspace of my space F. Okay, now my question is, Is line not passing through origin is a subspace or not? Is line not passing through origin is subspace or not? Think for a second and let me know. Will it form a subspace? No, right? Because when we speak about the subspace, it definitely has to have 0. So here also we had 0, right? So therefore here it is not passing through the origin, therefore it definitely doesn't form any subspace. Now coming to this example, here I am considering again in the same format, but the condition I am having A1 plus A2 plus A3 is equal to A4. So this condition alone I am changing. So similarly, first we are proving it contains the 0 element, or in fact it is non-empty, and then what we are doing is we are trying to prove alpha plus beta is also an element of H and C alpha is also an element of H. So while proving alpha plus beta is an element of H, we have to take two random elements from H that again forms the same pattern, that is A1, A2, A3, K, maybe alpha 1, alpha 2, alpha 3. Here I have taken x1, x2, x3, and here it is we are very particular about the fourth entry. The fourth entry is alpha x1 plus x2 plus x3. That is how we are taking, right? So similarly we are taking this also, y1, y2, y3 and y1 plus y2 plus y3 k, yn minus 1 yn. So while adding, I am getting again in the same format, therefore alpha plus beta will be an element of H, and similarly if you are able to find C alpha is C x1, x2, x3, xn plus x2 plus x3 k xn minus 1 xn, and again you can verify this also forms the same pattern that for an element to be there in the set H. Therefore C alpha is also an element of H. So we are able to prove alpha plus beta and C alpha is an element of H, and H has 0 also. Therefore H forms a subspace of F. And then the next problem, the next example, we are going to find the coordinate vector of 1, 2 or 1, 2 relative to span the set, the entire set 1, 1 and 1, 0. Now let us take a set H that's to be the span of the set 1, 1 and 1, 0. Definitely it will be a subspace of phi 2. So now 1, 2 can be written as this A multiplied by 1, 1 and B multiplied by 1, 0, right, because we are finding the coordinate vector of 1, 2 relative to this one. So I am writing this to be A multiplied by 1, 1 plus B multiplied by 1, 0. Now this gives me A plus B, 0, that is A plus B, A. So from here the value of A plus B is equivalent to 1 and the value of A is equal to 2. That gives me the value of B to be equal to minus 1. Therefore, the coordinate vector of 1, 2 relative to this span of this set is 2, minus 1. So we have obtained from this procedure. And then the next problem, here we are considering this matrix A to be 3 by 3 matrix 1, 2, 3, 1, 3, 4, 2, 4, 6, and we have to find the rank of this matrix. So how do you find the rank? The number of non-zero rows corresponds to the rank. So like that only we are here we are going to find. So I have taken the matrix and by row reduction, by row transformations, I am going to find its equivalent form and finally trying to reduce into an echelon form, and then I am going to count the number of non-zero rows. So here this is 1, 2, 3, 1, 3, 4, 2, 4, 6, and what I am going to do is I am going to change R2 to be R2 minus R1. So this is 1 minus 1 is 0, 3 minus 2 is 1, 4 minus 3 is again 4 minus 3, here I have to have 1. And then so 2, 4, 6 and all the remaining terms will be as such, and then here R3 is R3 minus 2 R1. So this is 2 minus 2 is 0, 4 minus 4, 2 minus 2 is 2 multiplied by 2 is 4, 4 minus 4 is 0 again, 6 minus 3 multiplied by 2 is again 6, that is 6 minus 6 is again 0. Therefore, here I am having the final matrix to be 1, 2, 3, 0, 1, 1, 0, 0, 0. I have already got the echelon form, so I cannot reduce it further without affecting its echelon form. So this is my final step. Here you can see the number of non-zero rows is only 2, Therefore, rank of this A is equal to 2. So, similar to this rank, this example, there are so many examples that is listed on the material and the solution is already there in the material. For example, consider this matrix. This is a 4 by 5 matrix. 2 5 minus 3 minus 4 8 4 7 minus 4 minus 3 9 6 9 minus 5 2 4 0 minus 9 6 5 minus 6. So, this is a matrix. For this, if you are asked to find rank, you have to follow the similar procedure whatever we have done here. Follow the similar procedure, you will be able to find the number of non-zero rows. So, here the number of non-zero rows would be 3 at the final step. Therefore, here I am telling the rank is equal to 3, and if you want to verify, please do that problem on your own, and the solution is already there in the material. Along with this, a number of examples is already there in the material. If you are very much interested, I would also recommend you to go through other textbooks and get some idea about the rank, and especially about the definitions that we have seen already, null space, dimensions, whatever we have applied here, subspace. Please learn that. I would strongly recommend that. We shall see another theorem. The theorem statement says, if a matrix A has n columns, then rank A plus dimension of null space of A is equal to n. This is called as rank nullity theorem. The next theorem states, let H be a p-dimensional subspace of In. Any linearly independent set of exactly p elements in H is automatically a basis for H. Also, any set of p elements of H that spans H is automatically a basis for H. We shall have a next theorem. That theorem says, let A be an n by n matrix, then the following statements are each equivalent to the statement that A is an invertible matrix. The first statement is, the columns of A form a basis of In. The next statement is, column space of A is equal to In. And third one is, dimension of column space of A is equal to n. And the fourth statement is, rank of A is equal to n. The fifth statement is, null space of A is equal to the singleton set 0. And the sixth statement is, dimensional null space of A is equal to 0. So, all the above 6 statements are equivalent to one another. Dear learners, so we have come to the end of the session. In this module, we learnt about the definition of subspaces of vector spaces, null space, column space, dimension and rank of a matrix. Numerous problems related to these concepts were also discussed. We have discussed these concepts with so many examples, and we have given various examples in your material for your own purpose. So, in the first part, we have discussed series of definitions, and in the later part, we have just given examples for few of them. I would personally recommend you to go through all the definitions and the examples and come back to the material again. We will see you in the next module. Thank you.